Welcome, everyone, to today's webinar on plate design in RISA-3D. Plates are one topic that we get a lot of different questions about in the program, and so I figured I would put together this webinar for everybody to go over a lot of the important aspects of plates. Now, for today's presentation, we're going to be using RISA-3D version 9.1.1, which is the latest version of the program, although actually the concepts relating to plates are going to apply to a number of previous versions as well. The topics that we're going to be covering today are shown on here. So the first thing we're going to be talking about, connectivity between plates. This is probably the area where the largest amount of confusion comes in when it comes to using plates. We're going to talk about shape limitations, submeshing, and how to improve the accuracy of your plate models. Of course, one of the most important aspects of plate modeling is the interpretation of results, so we'll talk about that. And then lastly, I'll show some sort of common situations where you may use some plates, and I'll show you how you would model with those. Now, the first thing to point out relates to plate connectivity. And what I would like you to know is that plates are not physical members. Now, when I refer to physical members, what I'm talking about is how members operate in RISA-3D. We have what's called a physical member. And with the physical member, that means that if you drop a node in anywhere along the length of a member, the member automatically connects to it. So, for example, the top chord of a truss that has multiple panel points can be modeled as one continuous member, and every web that frames into that truss will automatically connect to it. The concept does not apply to plates, though. Plates can only connect to other elements at their corners and nowhere else. So if you drop a node in along the edge of a plate, or along the interior of the plate, or anywhere other than the corner of that plate, as far as the plate is concerned, that node and whatever is connected to that node does not exist. A good graphical representation of that is what I've shown on screen here, this example. If we see here, I've got 3 plates drawn in this situation. I've got a boundary condition down here, and I've got a load up here. Now, here, this one plate has a node, N4, from these 2 plates that's connected along its edge. But these plates only connect to other plates at their corners and nowhere else. So at N4, these 2 plates are connected to each other, but they're not connected to this plate. So when I push up at this point, you'll see that a tear forms here. This actually sort of tears open, and you don't at all get the sort of load distribution that you would think of if your mindset is that these plates are going to be physical elements. Now, what you would ideally do in this situation is you would come in and you would submesh that bottom plate. And to submesh it just means that we're going to break that one plate into 2 plates. By doing so, every plate now connects to another plate at its corner, and you get full connectivity. You no longer get that tear, and you'll see that actually the amount of distortion of the plate element looks much better than it did under the previous model as I jump back and forth between them. So that's why we want to submesh. There's a variety of other reasons why we would also want to submesh, though. And for that, I'm going to pull up a model here that illustrates my point. So I'm opening up RISA-3D. And what we have in RISA-3D in this model is I've got a system where I have 4 columns and 4 beams and 1 plate element right in the middle. If I render this, you'll see a little more closely some wide flange columns, some wide flange beams, and 1 gigantic plate modeled straight in the middle of this. Now, if I double-click on this plate, what we're going to see is that it's an 8-inch plate, and its material is General Concrete 4NW. For a moment, I'm going to come in here to the materials spreadsheet. This is another point of common confusion within the program. If I come to the concrete tab, here we have concrete 4,000 normal weight, but that plate is not actually a concrete material. That plate is a general material. Plates, whether they in reality are built out of concrete, aluminum, steel, or anything else, are modeled as general in the program. What does that mean? Well, anything general within respect of RISA-3D, whether that's plates or even members, we do not give you a code check for. So we will calculate the appropriate and correct stiffness of your element. We'll give you all the forces and all the stresses in it, but we don't have any way to give you a code check because we wouldn't know what the applicable code would be. And that's how all plates operate within RISA-3D. Now, if you use wall panels as in lieu of plates, you can actually get code checks for things like concrete walls, masonry walls, so on and so forth. And when it comes to things like steel, there's not actually a direct addressing within the steel code as to how you would handle plate elements in the AISC, so therefore we really don't have a standard to tie to. But it's fine because we give you all of the appropriate stresses so that you can determine on your own whether or not something's actually going to work. So that plate is made out of a material that we had called general concrete 4,000 normal weight. And you note that for the general material, we don't ask you what your F prime C is. It's because we don't care. We're not giving you a code check on it. The compressive strength is irrelevant. What we do care about is your modulus of elasticity and your shear modulus. Also, the thermal expansion coefficient and the density are important as well. So I come back in here, and as I pointed out, I have an 8-inch general concrete 4,000 normal weight plate on these beams here. And what I've done is I've set up two basic load cases. I have a floor live load, and I have the self-weight of this slab. And for the self-weight, we're going to use the thickness of the plate multiplied by the density in order to figure out its weight. Now that plate is connected to the four corners of the columns there, and if I view my loading on here, I have what's called a floor live load of 100 pounds a square foot. And if I go ahead and solve this model for dead plus live, what we're going to see here, first off, is I get my reactions, so the load's coming down onto the columns. If I take a look at the deflected shape, we really don't see too much. But what I'm going to care about here, actually, is going to be the bending moment in these beams. And so for that, I can come up here, and we have this Member Results button. For those of you who haven't seen this, this appeared in version 9.1 of RISA-3D, but you can always add this in if you don't have it on your screen, and I'll show you how to do that later on during the webinar. What we're going to take a look at is the MZZ of the members. And the MZZ, for those of you who don't recall, is the major axis bending moment on these wide flange beams. So I'm going to turn that on. And what we're going to see graphically displayed is absolutely no bending moment appears on these beams. If I pull up a detail report for one of them, there's no bending moment. And if I take a look at a column, there's just an axial load and nothing else. The reason for that is because, as I mentioned earlier, a plate only connects to elements at its corners and nowhere else. So this gigantic plate here that has this 100 pound a square foot load, it doesn't connect to this beam because the beam is on the edge of the plate. The beam connects to the corner of the plate, but so does the column. And so what you're seeing here is the load in the plate basically short-circuiting the beams and going straight to the columns. Now we can get around that by doing something called submeshing. So what I'm going to do is come up to Modify up at the top, and I'm going to choose an option here, Submesh Quads. This is how we're going to modify the plates. And when I do this, I'm going to do a 2x2 submesh on this plate. Now, when we see number of pieces along A, B, and BC side, that just relates to the fact that when the plate is drawn, it's a 4-node element. So I clicked on 4 points to draw it, and A to B were the first 2 points I clicked on. So this is asking which direction we want to mesh it in. But we'll say go ahead and do a 2x2 submesh on all the selected plates. And I only have one plate on screen that's selected. By selected, I mean not grayed out. So when I hit that, you'll see what's happened now is we've turned one plate into 4 plates. Now this is going to increase the granularity of our solution, as it will, but keep in mind that in terms of the amount of solution time, the amount of memory this is going to use, our model is now effectively 4 times larger than it was before. But note that now these individual plates have nodes that do connect to the beams. So if I solve again, and we take a look at the moment diagram in this, now you'll see each beam on here has a point load style moment diagram, because what you're seeing is the fact that now these plates, which only connect to things at their corners, are now connecting to the middle, of course, and then they connect to the midspan of each beam and the column. So you're getting basically a two-way load distribution in this floor system. This still is not terribly accurate, though. What we can do is we can further submesh it. So if I come back up to Modify Submesh Quads again, we'll do another 2x2 submesh. Well, here we go. Now the model is 4 times larger than it was before. The model is going to take 16 times longer to solve than it did with our initial solution, but our results are going to be more accurate. What we're going to do is just keep submeshing this down and taking a look at the results that we get out of there. So I got 81 kip feet of moment in this last solution here. I had 80 in my initial, and if we keep submeshing this down, what we're going to do is we're going to converge upon a theoretical correct moment that's existing in these beams. So here we're at 89.9. Let's submesh quads again. And I'm just going to keep dropping this down. And what you're going to see is not only is this number both increasing and converging upon a final solution, which would be the theoretical two-way load distribution for this slab, but what you're also seeing is that the curve is smoothing out. Right now you can see it's a little jagged because that beam is only connecting to the plates every so often. But if I come back here, submesh again, and solve, now it's really starting to look much better. And you'll note that each time I submesh as well, that solution counter takes that much longer to run through. So here, when I did another 2x2 submesh, and I go ahead and hit solve, this is actually going to take a minute to solve here. Now in this case, we're only modeling one bay of a structure, so it's going rather smoothly. And there you go, we're at 91.7, barely any change in moment from the last solution. So as I keep submeshing, I'm converging upon a final solution. Now if I come in here at this point and go to my plate spreadsheet, which is in the data entry toolbar, what you're going to find is that in all that submeshing, I now have 4,000 plates in this model. Now that's probably overkill. I mentioned earlier that we're increasing the accuracy as we do each submesh, but there needs to be some sort of theoretical point at which you stop submeshing, because of course if we keep going with this, my computer's going to very quickly run out of memory. To show you how we do that, I'm going to pull up a separate model here. And this model that I have, I'm going to call my semi-rigid diaphragm model. Now the semi-rigid diaphragm model is a great way of illustrating a point relating to how we can use plates and how we can improve their accuracy. What I've done in this case is I've laid out this building with some concrete shear walls. And if I go ahead and measure that out, you'll see that's 30 feet in length there. So this is a 4-bay building, 30 feet by 120 feet, where I have a 6-inch concrete slab modeled, and I have these columns modeled as well. And what I'm doing is I'm treating this concrete slab as what's called a semi-rigid diaphragm. That is, rather than having it modeled as a true rigid diaphragm, for which we would use the diaphragm features in the program, I'm going to model it as plates to represent its true actual in-plane stiffness. And by doing that, we can find out how much deflection there's going to be in the diaphragm due to a lateral load that's placed on here. So here you can see I've modeled this lateral load as some 50 kip lateral point loads on here. Let's say that approximates some wind or some seismic. What we want to do in this model is we want to find out how much this diaphragm bows out within its own plane due to that lateral load. And by knowing that amount of lateral deflection on here, that would allow us to do things like design the connectors for the cladding or the walls that are on the outside of this so that the components in cladding, as an example, would not break off during a wind or a seismic event. And similarly, that if I had shear walls running in this direction, we would want them to be fully attached to the diaphragm even during a seismic event. Now note that I have these pin columns, so the diaphragm's just sort of going to be rolling along on top of these. They're not really going to have any additional impact on here. Well, I'm going to illustrate the difference between various submeshes on this, and we're going to decide at what point it's submeshed enough to give us valid results. So in order to do that, I'm going to create a few copies of this. So I'm going to come up here, and I'm going to create copies in the global X direction. I'm going to do 3 copies at 50 feet on center. So what we end up with now is 3 identical copies of the same building. And I'm going to do increasing submeshes on each one. So I'll snap into a plan view here. What I'm going to do is I'm going to unselect that first diaphragm, and I'm going to come up here and I'm going to do a 2x2 submesh on all the remaining ones. When I do this, you'll now see I've done a 2x2 submesh on here. I'm now going to unselect that model, do another 2x2 submesh. Now in practice, if you're trying to do something like this, you can always do it by doing a save as on your model as well, rather than doing the same copies within the same model. Either way, though, it works. And so here we can see the difference in granularity between each different model. Now at this point, I'm going to go ahead and solve my model for that lateral load. And what we're going to end up with here is a whole lot of results because, of course, now I have a whole lot of plates and a whole lot of nodes. But as we talked about earlier, what I really care about is the lateral deflection of this diaphragm. And for that, I want to take a look at my joint deflection spreadsheet. And in here, I can find out the X, Y, and Z deflections in the global axes of each node on here. But I have a ton of data to sift through. And I really don't care what the, say, Z deflection is for this particular node right here. It's irrelevant. We care about what's happening in the middle of the diaphragm, which is where we know the most deflection is going to occur. So what I'm going to do here is I'm going to unselect my model, and I'm going to pick out only the nodes at which point I really care about the deflection, which is just the center node opposite of where the load is applied. And if I come in here, I can hit this white exclude button. And what that's going to do is it's going to filter my joint deflection spreadsheet so that only the joints that I have selected are chosen. And what do we see here? Well, N73, should I come back and turn on my display of joint labels here? N73 is on what we'll call our coarse diaphragm. That one has a 0.078-inch deflection. And 53 here, we see we have 0.092. And so here we're looking at about a 20% difference between these two values. Now jumping from N53 to N33, here we've only got about a 6% difference between these two values. And if we go from N33 to N13, there's only about a 2% difference between these values. Now at this point, we're talking about a matter of engineering judgment. If you had this model right here, and you submeshed it, and your results changed by 20%, it's easy to say, okay, I definitely needed to submesh that one. Now, when you go from this model to this one, you submesh, the results change by 6%. Now, some folks would say, well, that's less than 10%. It's not a big deal. I'll stick with it. It really depends on where you want to put your cutoff point. Now, when I change from this model to this model, my results only changed by 2%. I would consider that to be largely negligible. Of course, once again, it's an engineering judgment call, so it's up to you. But taking a look at this, I would say that this model right here is completely unacceptable for representing our true deflection. This model here, also not really very good at it. Once we get to this model, though, our amount of change is relatively small, so I would say you can probably just stop right at this model and call it good. But definitely by the time you get to this model, there's no point in submeshing any farther. If you've done a 2x2 submesh, thereby making your model 4 times larger, and your results have changed by only 2%, you really don't need to take it any farther at that point, because you don't want to slow things down and bog down your solution. And more importantly, you don't want to have a large amount of results to have to sift through later on. And we're going to see that when we get into results interpretation. Now, for a moment here, I'm going to go back to my plate connectivity model that I had shown earlier to point out one other thing that's important. In the previous model, I had modeled a semi-rigid diaphragm in order to figure out what the lateral deflection of the building would be due to those lateral loads. One thing I see a lot of people do, though, is I see them model plates in order to get a gravity load distribution for a floor system in RISA-3D. But that's not really the best way to do it. You see, the problem is you have to submesh this plate down quite a bit in order to get the appropriate gravity loading to show up on those beams. And also, one thing that people frequently forget, look at this here, that plate is actually a physical element within our model. If I take that up to 100% renderings that we see where it goes, that plate is actually adding stiffness to our model, and it's acting compositely with the beam. So here we can see the plate coming in. Remember that everything is center line modeled within RISA, so that plate is actually existing at this beam center line, adding a bit of moment of inertia to it, which may not be very realistic. But it's also adding stiffness to the beam that may not be realistic. There's a number of reasons why having this plate in here may be the wrong way of going about it. Now, certainly if I want to design this as a floor slab, having that plate may be important because I'm going to want to get the plate designed for it. But if my only intention in this model is just to get an area load basically applied to account for my floor, what I would do in this one is delete the plate entirely and instead use the member area loading feature. And that member area loading feature right here is going to allow us to basically load the model without plates and do a two-way load distribution on it. So this is going to be a much more efficient way of going about it. So that's one thing that I definitely want to point out, is that using plates solely as a means of load attribution for gravity loading, would not recommend that at all. Let's go ahead and go back to the PowerPoint here and talk about some limitations behind using plates. Now, one thing we have to take a look at is the length, width, and thickness ratio of an individual plate element. A plate element is a 2D element. It's also known as a shell element. And there's important things relating to the aspect ratios on plates that can affect how correct your answers are when you solve with them. Now, plates are derived in terms of the solution in our program according to a mathematical formula. And that mathematical formula has certain bounds behind its assumptions. And so whenever you put together a formula to come up with these sort of things, what you're going to do is make certain assumptions, and you're going to say, okay, if the length to width ratio does not exceed 9 and the thickness to width ratio does not exceed 3, then the formula we use to derive all the plate values will be correct. Now, if your length to width ratio becomes 10, does that mean that the values that you get out of the program are incorrect? Not necessarily. All we're saying is that at that point we cannot guarantee that they're going to be correct for you anymore. And typically they're not going to vary wildly, but there's a lot of reasons why you're not going to want to exceed these values in the first place. So let's just talk about this real quick. What do I mean by length to width ratio? Well, in a rectangular plate, the longest side of the plate should not be more than 9 times longer than the width of the plate. Now, if you go back to some more old-fashioned plate formulations in older programs, what you'll find is that that value used to be about 3. But we've actually found ways to improve the plate formulation and get that all the way up to 9. Similarly, the thickness to width ratio now should not exceed 3. That is, that the plate should not be more than 3 times thicker than its least dimension. Let's see how this actually impacts things. If we take a look at the length to width ratio on these plates, what I've done is I've just sort of modeled a wall here out of plate elements. All of these plates here have a length to width ratio of 9, and that is within our acceptable bounds that we discussed earlier. So in theory, hey, this model is going to give us great results, right? Well, if I push on this, in this particular example, I got a lateral deflection of 2 inches. Now I submeshed each one of those plates 1 by 3 in order to get a length to width ratio of 3. Still well within our bounds, and of course both of these are giving us correct numbers. But here I get a lateral deflection of 3 inches, and this 3 inches is actually closer to the theoretical actual deflection of this wall. What's the reasoning behind that? The reasoning behind that is that even though these plates fall within the correct aspect ratio, their connectivity is very poor. Remember that the plates only connect to elements at their corners, so our only connection from one vertical plate here to another vertical plate is at the very top and very bottom of the wall, not along the height of the wall. So what you end up with is a series of vertical slip planes within this wall that greatly affect its stiffness. Whereas when we come over to this wall, because I have connectivity at the third points of the vertical plates on here, now these act much better together and give us a more accurate picture of what's going on. Now we'll also talk about the thickness to width limit. And so if we take a look here, this is a plate that's 3 times thicker than its least dimension. And we can see that representing it as this 2D element does seem kind of odd in this case. This is just supposed to be a 2D flexural element, and indeed if I load this plate, what we're going to get is a simple flexural formulation for how this plate is going to behave. So picture for a moment that this plate that I'm showing on screen is simply supported on both sides, and I apply a surface load on it. We're going to get a bending moment occurring within that plate, even though it looks like this. Now, if you start dealing with very thick plates, what you may want to do is go over to our 8-node solid element that we have in the program. You can get a solid element in the program by just doing a solid submesh of plates, And what that does is it turns it into basically a brick in the program. It's an actual three-dimensional element. And if I take this same solid element and I apply a surface load on top of it with that same simply supported boundary condition, what we're going to get is not really any bending in this plate. Instead, we're going to get a strut and tie compression arch occurring through the thickness of it. Because, of course, we can consider a much more accurate representation when we go over to the 8-node solid element. Now, you may ask yourself, well, why wouldn't we just use solids for everything? We could model all plates as just really short solids if we wanted to. And yes, it's true you can, but when you go to a solid, you're now looking at much more results to sift through. And in fact, because the quantity of results are so much higher, we actually can't present nearly as many of them to you. So in the case of solids, doing a design of something that plates could be used for would be very difficult. Although in order to get the correct stiffness and load attribution, if you have very thick elements you're trying to model, say a deep beam, concrete beam that's maybe only spanning 3 times its depth, something like a solid element may make sense in that case. But we're not really going to delve into those too much within the context of this webinar. It is something you can look up in our help file to learn more about, though. Another important thing to know about plates is that the shape is very important. And so here we have 3 examples of plates. I have a good plate, which is relatively rectangular. We have roughly 90-degree angles in here, and of course my aspect ratio limitations aren't being violated at all by this plate. We have what's called a bad plate. A bad plate is going to be one in this case that has an interior angle that exceeds 155 degrees, and that's going to be this interior angle right here. So in the case of this plate, what I'd probably be better off doing is modeling it as a triangular plate. In the program, we do support triangular plates, so if you're drawing a 4-node plate and you click the last node twice, it'll come out as a triangle, and that would be much more appropriate. We're going to see later on why shaping a plate like this is going to lead to some erroneous results. And then the last plate, of course, is the ugly plate. This one here has a bow tie configuration. So if I draw a plate by clicking on these 4 nodes right here, it's going to create a plate shaped like this within the program. Now, there's nothing in the physical world that can really represent what this is, but mathematically a plate like that can exist. Of course, mathematically that plate can also wreak havoc on the solver as well within the program. So I would strongly recommend never using a plate like this, because once you start introducing these into your model, you can really start causing a lot of issues. Fortunately, though, the only way to end up with a plate such as this is by drawing it yourself. Using our submeshing tools and such, you'll never end up with an ugly plate, so you don't have to worry about that too much. Another thing to consider on our models with respect to our plates is that plates only exhibit shear deflection. They do not exhibit flexural deflection. So note for a moment this plate that I have here that's basically cantilevered off from the left with a point load on the right. Now, if we took a look at how this beam would behave in reality, what you'd expect to see is that it would curve downwards for its deflected shape. But the edge of a plate cannot curve. I can't turn this plate into a curved element. By definition, all of its edges are straight lines that go from corner to corner. So when I push down on this, I'm going to get a very unrealistic portrayal of how its deflection is going to be. And we can see that right here, because of course it's just going to deflect down to this point and it's going to show us a straight line across. Now that can actually lead to some very unrealistic results when we get into the larger context of a model. So for that, I'm actually going to open up a new model here that's going to show off how inflection points with curvature has a big impact on how the program operates. Now what I have in this case is I have a model of increasingly submeshed plates, as it were, and we have all of the same materials and loading on each one of these. Now we come in here, what I'm representing in this case is I'm representing a 12-inch wide by 6-inch deep concrete beam that's spanning between 2 supports fixed at the ends, and you can see that right here. And what I'm doing in this case is I just have a straight vertical load applied to this model. And if I solve the model, what we're going to find is very different results, even though in this case we have the exact same material and the exact same loading applied to each one of these. I'm going to turn on my deflected shape so that you'll see what I'm talking about with this one. So when I view my deflected shape on here, what you're going to see very different behavior between each one of these. In this case, if I have a fixed beam with a uniform load across it, what I'm going to expect to see is a curvature that includes 2 inflection points. However, with this coarse mesh of these 3 plates right here, there's no way to capture that because, of course, this plate cannot have an S-curve shaped edge. And so as a result, our stiffness is all wrong in this model with only using 3 plates. Now, once we go up to 4 or even 6 plates, we still are not fully capturing at all that inflection point situation. It's not only until we get to about 12 plates in this particular model that we're actually getting it. And the key to this is that I have at least 3 plates between each inflection point that would be expected on here. Now, once I submesh down to this point, now we're getting even more accurate. And so the question does come back, okay, well, hey, you keep submeshing this down, you're getting more accurate. Why wouldn't you just take it to the next step further? Well, the reason in this model that I'm not going to take it any farther is because if I take a look at these plates that I have here, my plate length is now about 6 inches, whereas my plate thickness is 12 inches. So we have a roughly 2-to-1 aspect ratio in terms of thickness to width, and remember that we don't want to violate that 3-to-1 on here. And at this point, really, with these square plates on here, we're getting pretty good results. So I would probably stop it at this point. But it is important to note that had we left this very coarse mesh in our model, we would have gotten results that were very unreliable and didn't exhibit the true behavior of a system such as this. So now we have an idea about how plates work with respect to how we should size them and shape them and such. Let's talk about how to get results out of plates. And of course, afterwards, I'll go back and show you how we would actually draw the plates. So when it comes to results, we're going to take a look at this sample plate that I've drawn on here. And what you need to know is that a plate has local axes. Now, these local axes have no correlation to the global axes within the model. Instead, these just allow us to get forces reported relative to the plate itself. What you'll see is that the plate has its own local x-axis that runs along this edge, its own local y-axis that runs parallel to this edge, and its own local z-axis, and the z-axis is always perpendicular to the plate. Now for plates, we give what's called plate forces, and one of the plate forces is the F sub x. And Fx is an axial force that exists within the plate, and it's running along the plate's local x-axis. Similarly, we have a force that's called the Fy, and that is a axial force running in the plate's local y-axis. So we're going to report both of these to you, but we're also going to report another force to you, and that force is called the Fxy. The Fxy is a force that exists within the plate that's occurring simultaneously in the local x and y axes, and it's trying to turn the plate into a sort of diamond shape. And when it comes to doing design of the plate for axial forces, what you actually need to use is Fx plus or minus Fxy, and Fy plus or minus Fxy. And when I tell you the plus or minus, what I'm saying is take whatever the more conservative of the two values is, because this is an additive force that also exists along with the Fx and the Fxy. Now, aside from those, we also have shears in the plate. This is an out-of-plane shear, and this would be a shear that's running along the local x-axis. That's called the Qx. And similarly, another one that runs along the local y-axis, that's called the Qy. Now, there is no Qxy because shear doesn't have a similar correlating force that goes along like that. Now, another thing to consider is a bending moment within the plate. And this is going to be a bending moment out of plane from the plate. What we have here is a bending moment about the plate's local x-axis. Now, there is a sign convention that was determined back when plates were originally formulated, and it can lead to a lot of confusion, but basically, a moment about the plate's local x-axis is called an my. Now, I assure you, this is nothing that RISA came up with. This is just something that's in the textbooks, and we're following standard convention on this one. And when it comes to interpreting plate results, I often just remember that the moment that's reported is the opposite of the one that I would expect. So a moment about the plate's local x-axis is called an my. Similarly, a moment about the plate's local y-axis is called an mx. And similarly to the plate forces, we have a simultaneous moment occurring in both directions that's trying to fold this plate into a taco. That is called an MXY. And so if I wanted to know what my maximum moment was about my local y-axis, that would be equal to mx plus or minus mxy. And similarly, the maximum moment about the local x-axis would be the my plus or minus mxy. So once again, very important things to consider. The other important thing to consider, aside from plate forces, is going to be plate stresses. And so for that, I'm going to go ahead and open up the model so that you can see that you don't actually have to rely on my webinar handouts in this case. If I go up to Help up at the top within the program and choose Help Topics, what you'll see is that under the left under Contents here, we have a big help topic on plates. Now, those of you who have the printed general reference manual can also read about it in print within that manual, but that's basically a direct printout of what we have in here. We have all sorts of great information about how to draw plates, how to use them, and everything else. And one of the topics in here is the plate results topic, which I'll frequently come back to when I'm using the program just as sort of my own personal reference. Now, the forces are pretty straightforward. The stresses in the plates are a little more difficult. We have a sigma x and a sigma y, which are bending stresses that are occurring along the local x and the local y axes within the program. What we'll also report to you is a sigma 1 and a sigma 2. Now, those of you who remember your old mechanics and material class and Moore's circle will recognize these. These are your principal stresses that are derived based off of your sigma x, your sigma y, and your tau, which is going to be your shear stress. Now, all of these stresses form together, and they're very powerful if you know how to use them. And different people who use plates for different things know very valuable ways to use them. So people who design pressure vessels, for example, care very much about certain sigmas, whether that be the sigma 1 or the sigma 2. For those of us who are just a little more novices with the plates, though, one stress that you may consider, and one that I use all the time, is what's called the von Mises stress. And you can think of this really as a square root of the sum of the squares of all the stresses that occur within the plate. The von Mises is a unidirectional stress that can be used to compare against yielding in an elastic material such as steel. And we're going to see later on how that could be useful. But for now, what we're going to take a look at is how we can use plates to design a concrete slab. So in this model that I have here, what I have is I have a concrete column that's been modeled. And this concrete column here is resting on some plates. I'll go ahead and snap into a view here so that we can get a closer look at it. Now I'm going to go into a plan view for a moment here so that I can unselect this column. And we're going to draw a couple of plates in directly underneath it. And give me just a moment here to prep this model. All right, so where this column comes in, I left a couple of plates out in here so that we could actually draw them in on the model. So I was going to show you, if I double-click on these, you'll see that I have these 8-inch concrete 4,000 normal weight plates. And I'm going to come back in here, and I'm going to draw these in. And all you need to do is come up to Draw Plates, pick out your material, pick out your thickness. Note that we have release codes so you can pin the corners of plates, and that determines how they connect to each other out of plane. And I'm just going to draw in a few plates that are right on here. The reason I'm drawing these in is because our local axes are going to be affected by them. Now, when it comes to operating with plates, one thing to consider is the local axes. I'm going to show you guys some buttons that are available within the program. They don't show up by default, but they're very valuable when it comes to plate modeling. If I come up to Tools up at the top of the program, I have this Customize Toolbar option. And in here are a variety of buttons that I can add to my toolbar up at the top that I may not have known existed before. And when I add these in, they'll always be present within my machine that I'm working on. So here I'm going to come in, and I'm going to add a Plate Property button. And note that when I click Add, it creates this new button up here. And we're also going to do a Plate Force Contour and a Plate Stress Contour button. People who use plates a lot will usually have these buttons set up right here on their toolbar so that they can use them. And if I come up here and click on this black drop-down arrow next to Plate Properties, I can take a look at things like the plate label. Each one has its own number. But more importantly, I can take a look at the plate local axis. And so when I click on that, what we'll see is that the local axes of many of these plates are aligned with each other because I actually created this as one giant plate and submeshed it. But if we zoom in close, you'll see that some of these plates are oriented in different directions. Now this can cause us issues. For example, the local x-axis of this plate is different than the local x-axis of this plate. And so if I start comparing values of, say, our f sub x, I can't directly compare the values back and forth between this plate and this plate because that value is reported local to the plate. But I can come in and correct these values at any time. If I come up to my draw plates and go to modify plates, you'll note that we have this rotate local axes option. So one thing I can do, for example, is an out-of-plane flip, where if I click on these, now it's flipping the z-axis to be pointing downwards. Now another thing that I need to do is I need to come in and I need to do what appears to be a counterclockwise rotation on a few of these plates right here. And in this one, I'll hit it twice. Now we have the plate local axes oriented. We're going to take a look at the plate local forces, so it's very important that I have these all oriented in the same direction. That's why I've done this. Now I'm going to go back and shut off those plate local axes so that we can take a look a little more closely at what our model is here. I have an 8-inch concrete slab supported on all edges by these pinned boundary conditions, but this slab has no interior support. And on top of that, I've got this concrete column here, and that concrete column has a 30 kip point load on top of it. What we're going to do is design the concrete plates that are in this model to support that point load. So the first thing I'm going to do is solve the model. Now when I solve, we can take a look, for example, at the deflected shape to see how this happens, and you'll see the column is pushing down there in the middle, and we're in the rendered view here. But another thing we can take a look at is the moments that are reported by the program. So if I come up to my Show Plate Force Contours, let's say that we want to take a look at what moments are present in the slab here. I'll take a look at my plate local axes. I have to shut off the deflected shape to see them. And if we want the moment that's about the global x-axis, what we're going to want to take a look at is the moment that's about the plate local y-axis, but remember that's called the m sub x. So in this case, it just happens to correspond, but it won't always. So we're going to take a look at the mx. Note that this is a lowercase x. Lowercase means that this is reported about the plate's local axes, not about the global axes. And what we get here is we get this moment distribution that's shown in our model. And if I drag these toolbars out of the way, in the upper right corner, we have a color coding legend that shows plate moment X, and this is reported in kip feet per foot. When it comes to plate forces, we always give them to you in a per foot of plate basis. And so what we can see is that the red represents a 17.7 kip feet per foot moment. But note where that moment's occurring. It's right here in the middle of this slab. And I have this giant spike, basically, of the moment right at the intersection of these four plates. Well, in this model, I have a 24-inch by 24-inch concrete column, but remember that everything is centerline modeled. And so what we're dealing with here is the fact that that 30 kip point load for that column actually comes down at a tiny little needle point right here in the middle of my slab. That's not terribly accurate. In reality, the panel zone of this column is going to sort of evenly distribute that load out, and what we care about more is the moment at the face of the column. So I'm going to come in here. I'm actually going to modify this by by adding in rigid links to this model. So I'm going to come up here, and I'm going to draw a general member, type rigid link, which is a section set called rigid. And these are going to be more or less infinitely rigid little bar pieces that are going to run around the perimeter of the column, and they're going to connect the middle of the column along with the plates. So that now, when this point load comes down on the column, it's going to spread that load out all the way to the perimeter of the column, and we're going to get a more accurate load distribution. Now remember when we solved before, we had a maximum moment of 17.9 kip feet per foot. Now all of a sudden, that maximum moment drops way down to about 12.5 kip feet per foot. So a big difference there. But what we're also seeing is these crazy contours that are occurring within here. And this gets into one of the most important points of the plate webinar, and I cannot stress this one enough. The contours that are reported by the program are not to be used as design numbers. Contours are only intended to give you a ballpark figure or a ballpark concept of what your moment's forces and stresses are. The reason for that is because we need to get basically a pretty picture shown on screen here, and we do that by employing something called a smoothing algorithm. So we take the force that's present in each one of these plates at points that are called Gaussian integration points. There's 4 points inside of each plate. They're about a third of the way in. And based off a plot of all these different plate forces, we come up with contours to figure out what all the forces are and show them to you graphically. Now, the issue we have is that the plate forces in this plate right here, for example, are going to have our absolute maximum moment present for the whole model. This plate, though, is actually going to have 0 plate force. It's entirely surrounded by rigid links, and so by definition it can't have any force. Now, how do you draw contours where we go from 0 at this point to the maximum value in the whole model at this point? Well, you have to cram a lot of contours in between there, and then in order to make it actually look reasonably decent, you have to smooth it out and sort of spread these contours in towards the middle. So these contours are not actually accurate values, and they shouldn't be used as such to reflect that. But we can improve the contouring a bit by getting rid of these 4 plates, which are effectively 0 force members because they're entirely surrounded by rigid links. I'll do that by coming in here and deleting these 4 plates, so that all we have left now is the column coming down where its rigid panel zone is. And when I solve at this point, now what we're going to see is that 12.7 kip feet per foot is listed as the contour moment. Now, is that our maximum moment? No, but it's probably roughly what it's going to need to be. If we're going to actually design the rebar in this slab, though, we're going to want to come into the plate forces spreadsheet, because the spreadsheets are where we get the true actual values, the design values. And coming in here, we can see we have all these plates reported. Rather than trying to figure out which plate is which, a quick and easy way of me going about this would be to highlight the MX column. And what I can do is right-click and say Sort. And I'm going to sort this column from absolute max to absolute min. And here we actually have a maximum of 13.84 kip feet per foot that's occurring in this plate. It's just that in order to spread out these contours and make them look better, the red contour shows that the average plate moment in this whole red zone is about 12.7 kip feet per foot, even though 13.8 is the maximum. And don't forget that when it comes time to design in here, that we're going to want to also do a plus or minus with this MXY. So our true design moment would be 13.8 kip feet per foot plus or minus about 1.8 kip feet per foot, to result in an actual design moment of about 15.6 kip feet per foot for these plates. Now, that's all well and good for these plates right here, but when it comes to actually designing in concrete, we don't care so much about an absolute maximum moment at this one point right here, which is basically what's being reported to you. Instead, in concrete design, what we tend to do is we smear out the moments in order to get design strips, as they're called. And so in this case, I would want it to design what's known as the column strip in this model. Now, if I flip over, we can also take a look at the MY that's running in this direction. I'm going to get a design of this by using what's called our internal force summation tool. If I unselect the entire model here, and I grab only the plates that I would consider to be part of the column strip, and in this case, that's going to be basically everything that exists right here within this, let me just measure it out real quick here, 6-foot wide strip that runs underneath the column. What I'd really like the program to do is tell me what is the total moment in this strip of plates here so that I can design the rebar for that, rather than trying to design each piece of rebar localized based off what a maximum moment may be exactly where that is. For that, we're going to use the internal force summation tool. When we use this tool, it's important that we're snapped into an exact plan or elevation view. So here I'm in an exact plan view. And I'm going to come in and I'm going to do a cut on this. I'm coming over and picking out this tool on the left. This is a blue sigma with a red arrow in it. And the program's asking me to pick cutting points. I'm going to pick any 2 points here by clicking to create this red line. As I drag this red line, note that right down here, we report an F1, an F2, and F3, and an M1, M2, and M3. These are moments reported relative to the line that I've cut. And if I click at any point, I'm actually going to get a dialog box here that shows me that when it reports these forces and moments to me, that the y-axis was defined by the user. That was me. So when I click these 2 points, that red axis is the y-axis. Therefore, an F1 would be a force along that axis, and an M1 would be a moment about that axis. And this is going to be the maximum force and moment net summed up over all these elements that I have selected. And I point out the selection because I say if we had other parts of this model selected, it would also be summed in here, and that would give us basically inaccurate results. And so here my F1 is 0, and of course I would expect my net moment in this, or net force to be 0 here. And where I did this cut, my net moment is about 12.98 kip feet. And this is straight up kip feet, not kip feet per foot like we were getting in the plate forces. And so that would be my design moment for this strip. So now I know that M1 is what I'm really going to care about in this case. So if I come back and do that cut, we're going to follow my M1 value. Now note also that the F3 is the amount of shear, and that as I move along here, the moment in this column strip is about 0 at the edge of the slab. And as we move all the way up to the face of the column here, we've got about 80 kip feet of moment that's existing on there. Let's just say 79 right here. And so once we get past that, of course, these values would represent what the moment is directly underneath the column. But remember that you're really only going to design the rebar for what's occurring at the face of support here. And so we're still sort of doing all this by hand. And so if I have a 78 kip foot moment over this whole strip, what I'm going to do is just use the old-fashioned conservative method of designing rebar for bending, which is the MU over 4D method. So if I have my ultimate moment, 78 kip feet, divided by 4, and then we're going to divide that by the D of the slab. It's an 8-inch slab, so let's conservatively say that the D is only 6 inches. We end up with 3.25 square inches of steel that I need to run in this direction. And if I divide that by the area of a number 6 bar, what it tells us is 8 number 6s running in this direction should be sufficient to be able to handle that moment. Now, of course, I'd also want to check the shear as well, and I can compare the F3, but in this case, seeing a shear of about 12 kips or so along a width of about 6 feet, that's only about 2 kips per foot. That's nothing much to worry about in the case of this slab. Now, it is important when you use this internal force summation tool that you're in a plan view or an elevation view. And the reason is that we report these values relative to the direction you're looking at the model in. So if I snap to an isometric view, note now I have M1, M2, and M3. Because what we're doing is we're showing you the moment relative to a vector sticking out of my screen, not relative to the model in any way. Now, you can get a lot more information on that internal force summation tool out of the help menu if you like. At this point, though, I'm going to move on to a couple final models just to prove another couple points to you about how plates are working within the program. And this has to do with how we would actually model plates. So I'm going to come back in here and I'm going to create a new model. And what we're going to do is we're going to model a cylindrical tank here. To do that, I'm going to use the structure generator that's built into our program. Some of you may have seen this before. I'm going to come to the Insert menu up at the top, and I'm going to come down here to where it says Structure Generate. And let's say that I want to generate a cylinder made out of plates. Well, if I scroll down here, I can pick out cylinder. And this is going to ask me all the information about the plate generation we're going to do. So rather than drawing the plates individually, I'm just going to generate them. And so I want to generate this about the global y-axis with a radius of 20 feet. And I'm going to use 12 sweep increments. And you're going to see what this means once I actually generate it. I'm going to tell it that I want to have plates, but I don't want to have any stiffeners on here. And I want my plates to be made out of general steel, 1/2 inch thick. Now, when I hit OK, we come in here, what you'll see is that it's generated a tank out of plates that's a 12-sided tank. That was the number of sweep increments. Now, if I was trying to simulate a cylindrical tank, this is a very coarse, rough approximation of it. And what you may do in a model such as this is you may generate this and look at it and go, oh, no, I need this to be more accurate, and look at these plates. They have really big aspect ratios. What I'll do is I'll come in and I'll submesh this model, and I'm going to do it 10 by 1, And when I submesh it, oh great, all right, now we're going to have a much finer model. That's going to be fine. Well, it's true, each side of this tank now has a finer mesh, so it'll be more accurate, but don't forget that the original premise that we started out with, that this is a circular tank, submeshing it doesn't make it any more circular, because the program doesn't remember that, of course, you're trying to approximate a circle. So creating something coarse and then just submeshing it this way isn't really a smart move within a model like this. Instead, what I probably want to do is I probably want to hit undo here and go back, and if I want a finer mesh, I should also be sure to generate this with more sweep increments. So instead of 12, say, let's go to 120 sweep increments. And now this will approximate my circular tank as a 120-sided polygon. So when I hit OK, there we go. That's a much smoother layout, and now it's going to approximate circular behavior much better. Now at this point, I'm going to go ahead and load this tank up. So I'm going to come in here and add some boundary conditions along the bottom. And then we want to apply a surface load within this tank. And to do that, I'm going to apply plate surface loads. So I'm going to select, say, the bottom 4 plates here. We don't have a way of applying a tapered surface load, but what we can do within the program is we can apply a regular surface load to each plate, and we can manually taper it by stepping the load down as we move up the tank. So for my surface load, you click here to draw surface loads. I'm going to do a direction of lowercase z that's going to be perpendicular to the plates. And I'm going to do a magnitude of 250 pounds a square foot and apply that to all those plates. So now when we come in and look at it, say from an overhead point of view, you'll see what that looks like. A uniform outward pressure of 250 pounds a square foot. Now I'm going to come up and grab the next 4 plates, or let's just say the next 3 plates in this case, coming up the height of this thing, and I'm going to step that load down to maybe just 200 pounds a square foot. And it's up to you as to how much granularity you want to add into the stepping of your loads, but this is basically how you would go about it. And the last one we'll do there is 150 pounds a square foot up along the top. So now I have this stepping load that's occurring in here, and I just added those loads to basic load case 1, so we'll just solve basic load case 1 with a factor of 1. And take a look at what our results are. And in here, let's say that I wanted to design this tank for, say, rebar that's running along its circumference. And so what we're going to care about is what would be known as the hoop stress. Well, in this case, I can't really get a very good stress reported out of this. My stress results all typically relate to things like bending or a von Mises stress, which isn't going to be as directional as hoop stress. So I'm going to come up here and take a look at my local axes. Oh, we can see this is my local x-axis. What I'm going to care about is my F sub x. So if I come up and take a look at my plate forces, the Fx, according to the contours, is about 5.73 kips per foot. And if I take a look in the plate forces spreadsheet just to see what the true maximum is, I can come in here and sort this. Absolute max to absolute mid. There's 5.318 kips per foot. Remember that we have to do plus or minus fxy, but that value is 0 here. And so if I wanted to know what my hoop stress is, I would simply say that, okay, we have this 5.31 kips per foot on here. And we would come up here and say that that 5.318 is going to be divided by 12 inches, and then further divided by the ½ inch of plate thickness, for a total of 886 psi. So that would be our hoop stress. We can basically take forces and turn them into stresses just by making sense of it. Now I have one more example to show you before the end of this webinar, and that's going to be a steel design. So I'm going to come up here and I'm going to create a lifting lug. So let's think of plates also as being able to be used for very small elements in design. Such as a lifting lug. And in this case, I'm going to do one. It's about 14 inches by 10 inches. And we're going to presume that we're going to be attaching this to something and lifting it and finding out whether the steel is going to yield when we do that. So I'm going to come in here and I'm going to set up a section set briefly. I'm going to call it my dummy section set, and I'll explain why in a moment I'm doing this. And what this section set is going to be is a 1/4 inch by 1/4 inch rectangular piece of steel. Okay. So I want to set up points to snap to within my model, and when we talk about dealing with a very small model such as this one, I actually want to switch over to be in inches instead of feet when I'm working with it. So I'm going to come in here, and I'm going to use my structure generator once again. I'm going to generate a circular arc within the model. And what we're going to do is a 90-degree sweep on this with a radius of 4 inches along 8 increments. And I'm going to do a dummy section set for this one. So I'm going to hit OK. And what we've done now is in the program, I've created this arc of members and points along here that form this 4-inch radius. Then I'm going to come back and I'm going to generate the outer arc, as I'll call it. And so we'll come back in here using the same settings, but this time without any dummy members, and using an 8-inch radius with 16 increments. Going to hit OK. Here we go. Now here's our outer point that's along here. That's 8-inch, that's 4-inch. I'm going to come in, select this inner point, and I'm going to use the mirror command within the program to actually mirror that about the global XZ plane so that now that points downwards. And I don't actually need my dummy members for this lower portion, and you'll see why here once I get to it. So I'm going to delete all of those members. So we just have some members along here. Next, I'm going to copy this node down a negative 14 inches. And I'm going to copy this node down negative 10 inches. So now we have the outline of half of a lifting lug. In order to draw this, I'm going to use what's called our auto mesh feature. There's sometimes a lot of confusion about auto mesh. And if I come in here, auto mesh doesn't mesh existing plates. It's used for drawing new plates. So what I did was I went up to Draw Plates and went to the Auto Mesh tab. What I want to do is I want to create a mesh of general steel plates that are 5 inches thick, and I want these plates to be no less than ½ an inch per side. And now I can come in and I can draw a polygon. So I'm going to hit every point that's along here. And what's going to happen is when I close out that polygon, the program is going to automatically create a plate mesh internally in that polygon for me. And that plate mesh can then be used to actually load up this model and represent it. So I'll come back, double-click on the last point, and what we end up with here is a mesh, as you can see inside. Now this is a very fine mesh, and because we're going to be working with such small values, I may want to come to my global parameters and reduce what's called my merge tolerance down so that it doesn't affect things as badly. Now I can come in and I can mirror this about the global YZ plane. And so there's my lifting lug laid out. Now I'm going to come in and I'm going to add in a fixed boundary condition at the base of this, and we're going to add a quick load to it so that we can see how it's affected. There's my fixed boundary condition. And actually I need to zoom in a little closer because we don't want it all the way at the bottom. And then I'm going to add a load to the members. The reason I drew these dummy members in here is because I want the member to span from plate to plate. And so I'm going to put in an 80 kip per foot vertical load on these members right here, and these members will attribute that load to the plate automatically. And once I have that, then I can just create my loads, and I can solve my model. And once I solve the model, I would then just come in here. I would get my von Mises stress reported out of here. And as long as the von Mises stress reported, and remember that's the maximum universal stress, is going to be less than the yield stress of this plate, 36 KSI, which I haven't entered, but which I would just know, then I know everything's going to be all right. So that's the idea of how you use plate modeling. And you can see how putting these together can really make the program quite a valuable tool for you for a variety of things, anywhere from tiny little connectors like this all the way up to big plate or tanks, concrete slabs, and everything in between. Now, we do have additional resources available, as I pointed out. There's a whole lot more to read about plates than what I was able to cover in this hour, and you can find those in our help file and our printed manual. And also, I have a number of great articles I've written up on plates that are available here on the RISAnews.com website.